So I'm going to try to give some basic ideas about radiation shielding for space radiation, and then I sent Sydney a link to the computer codes we have at our shop in JSC. I might have time to mention there's also a good site at NASA Langley, the Alteris. I think Charlie knows about Alteris with Lisa Simonson and that group there. So I probably won't have time to talk about it because I have a flight later, but I'll give you a lot of the background information, and then you can contact us about getting copies or some of the codes. Now you just log in over the internet after you're approved for ITAR, which U.S. citizens and space station partners, that kind of stuff. There's like a form you have to fill out. So, okay. Oh, yeah, the mic. Okay, so I think you've heard all this about the quantities and units, but just a quick review. HZE is, or HZE, and if somebody's from England, right? It always sounds better than HZE. High charge, Z number, and energy. It's not the charge, it's the charge number. To be precise, fluence, the number of particles per unit area, and linear energy transfer is the rate of energy loss, and that's different than energy deposited. It's units of, usually we talk about kV per micron in tissue is the unit. And then range, I'll talk a little bit more about range, but range is the average distance traveled before the particle stops. So if you want to stop a particle, if you know its energy, you can look up its range, and then you know how thick the shield needs to be to stop it completely. You just have to worry about secondary radiations, and can you have something that thick? The absorption cross-section is the probability of a nuclear reaction expressed as an area. So these are going to be very small areas because they're characteristic of the size of a nucleus, which is in Fermi squared, femtometer squared, or millibarns, or barns, very small, 10 to the negative 26 squared centimeters is the size of these cross-sections. And then the dose is the fluence times the LET. There's a conversion factor there I haven't listed, but that gives you units of Gray, kilograms per joule, or joule per kilogram, sorry, and then that's all equal to the old unit rad. So Gray is SI units named after a famous scientist who helped discover radiation, Gray, and then rad is the old unit. RBE, we talked about that in quality factor, and then dose equivalent is not really a unit, but you use sieverts, and that's equal to 100 of the old unit REM, or radiation equivalent man unit it was called. Okay, so there's two different types of transport codes. So if we really wanted to get into a shielding business, you need to use a transport code. So one type is called a Monte Carlo simulation, where they follow particles. So they follow a particle, and then they look at a probability that it had a nuclear reaction. So use the absorption cross-section. Say maybe take a step of a half a gram per centimeter squared, and then you say, did a nuclear reaction happen? If nothing happened, you just let its energy be degraded by the dE by dx. If a nuclear reaction happened, then you say, so use a random number generator to test that absorption cross-section. Then you say which nuclear reaction, what's its new angle, what are the new particles, and you can have like 30 new particles created at the nuclear reaction if it's really violent, or 2 or 3 if it's kind of mild. Then you give each one of those an energy and an angle based on other types of cross-sections. So that's what they do. And these codes, there's 3 main ones. There's GEONT4, that's from CERN. And then there's FLUCA, that's also CERN, but a lot of INFN labs in Italy. And then there's one in Japan called FITS. So these ones take some more training. They're kind of slow. Some of the computer runs might take a week. But then there's the NASA codes, which are based on solving the Boltzmann equation. So the Boltzmann equation is an analytic approach to describe these same processes. And these codes take minutes. So that's the one on the Alteris website. And some of the codes we use on risk for cancer risks or acute radiation risks are based on those codes. And they can run on your laptop in minutes and over the internet very quickly. And they're very accurate. I'll show you some examples. So that's like a one-dimensional Boltzmann equation. They have John Wilson is from NASA Langley, spent his career, or a lot of his career, figuring out nice ways to solve those equations and building up the databases for cross-sections and stopping powers. Okay, and then the quantities, once you know, so the solution of the Boltzmann equation is the flux. So it's the number of particles, the phi of j, at a given position in the shielding of a given energy. So j is the particle type, It has an energy and its a spatial position. And then on the right-hand side, you have the interactions that produce new particles. And the new particles can be produced by any particle K, as long as you conserve mass and charge in the nuclear collision. So this is the Boltzmann equation. But once you know that phi of j at any position in the shielding or in your tissue, then you integrate over that to get the dose or the dose equivalent, and then the dose equivalent is used in the risk calculation. So the dose, I'll use two spatial dimensions, x and z, one for the spacecraft shielding or the planetary shielding, and one for the tissue shielding. So you might have a big matrix of doses at all these different points you're interested in. But that's just going to be an integral over the spectra, these flux spectra, folded with the stopping power. And so the flux is the number of particles per unit area per unit energy. And you can add time per whatever time unit you like to use. And you fold it by the d by x, and you integrate over all the energies, and you get the dose. And then if you fold it by the q function, so q is a function of LET in the old model, but in the new models I mentioned this morning, it's particle of particle type and the energy. You integrate that over to get the dose equivalent. I don't have time, but then the effective dose is you're integrating over all the tissues. So each tissue gets a weight. The lung is the biggest because that's a big target, and it's got a major part of the cancer risk. But there's lots of other tissues, about 12, that the ICRP recommends, and NASA does it a little bit differently, where we're using age-specific and gender-specific weights rather than the ICRP is using gender-averaged and age-averaged tissue weights. So it's a little bit imprecise in that sense, but they're really using it for a certain regime, and they didn't really invent this effective dose approximation for the space conditions. That's also another new report that's coming out from the ICRP. It's going to be published online in July for public comments as the first report by the ICRP on space radiation. And it's all about the exposures and the organ doses, and I'm a member of that committee, so they're going to recommend some new things for the ICRP. Okay, so just quickly, this HZ train code, it has about a 20% accuracy in absolute predictions for physical dose and dose equivalent. And then here's an example of a proton and I think deuteron spectrum, so it does pretty well. This is a pretty challenging test, these spectra, because these are GCR protons that are below the Earth's magnetic cutoff. So they're strictly secondary protons. They weren't there in the primary spectrum, so it did a good job predicting these secondary particles. And this just shows you for a lot of shuttle missions and space station missions and Phantom Torso missions, the level of accuracy, so I say 20%, but it's actually a little bit better than 20% if you see the error listed there. So that just gives you some background. These codes I'm talking about can make these type of predictions. They're not fully tested for other materials, but we did do some experiments on the space shuttle with polyethylene spheres in the shuttle payload bay, the aluminum spheres, and then you have the spacecraft itself, which is mostly aluminum. So for those types of materials and the Phantom Torso tissue equivalent material, it did pretty well. Okay, so I remind you about the charge distribution of the particles. Yesterday that I showed you this. So we have to be able to transport all these particles through the shielding and into the body if you want to see the effectiveness of shielding or the atmosphere of Mars. And that's what everyone here is interested in, is to try to think about how to solve the Mars surface radiation problem. So you have to transport all these particles through the Mars atmosphere, but there's also the energy, which I'll get to. But if you look at the LET versus the energy, you can see each particle has its own curve. So when Nathan was talking this morning about the detector, you know all this information going in, and that's how they resolve which particle was in the spectrum of the crater instrument. And you can see what happens is why does the LET go up as the energy goes down? Does anybody remember why that would happen? So what you had to think about. No, this doesn't have to do with secondaries. It just has to do with, you have a particle coming in, it doesn't have any electrons, just a nucleus. It's going to interact with a target atom. So what's really going on is it's the velocity of the orbital electrons of the target atom. It's the important thing. So when the particle is very high energy, it just goes by the target atom so quickly, and you see it becomes like a constant at high energy, that it's independent of the particle energy, because to the target energy that's going to interact with it doesn't really matter if it's 90% the speed of light or 95%. It's just so fast going by, because the orbital electrons, their speed is like 0.1 to 0.2 of the speed of light. So then as you go down and the particle energy is matching the energy of the orbital electrons of the target atom, it's got more time to interact, so there's more ionizations and more energy loss. And then as you go even farther down, I don't show here, it's the opposite. Now the particle is going to move slower than the orbital electrons, and then you're in a different regime. But that really doesn't matter too much for NASA, because those particles don't even penetrate 1 or 2 cell layers. They just are at the very end of their range and stop. So that's a key quantity, is the LET. How's that changing in the shielding? So you slow the particles down, their LET might go up, and which could be good or bad, depends on the quality factor. And then the range is just expressed as the integral of the energy over the stopping power, or the dE over the stopping power, and you integrate from 0 to the initial energy of the particle. And this curve shows you for different charged particles, 1 through 26, I guess, through iron. I can see through here. Let's turn it off. What the range is for different materials: hydrogen, water, and aluminum and lead. So you can see how that range is changing for different particles and different particle types and different energies. And then there's a very simple law that comes out above a few MeV that this holds very accurately, that the range of any particle Z is equal to the proton range times the mass of the particle divided by the charge squared. So the proton is going to have more range at the same energy than iron or carbon, because that A over Z squared is going to be less than 1. Question?
Yeah. So if you go back to the previous slide, can you give an estimate of what it means to go from LET of, say, 0.1 to 1,000 in terms of like risk increase?
Okay, so the quality factor, if you remember, the ICRP model, everything below 10 kV per micron has a quality factor of 1.
Okay.
And then it rises linearly to a peak at 100, and then it declines. So at 100, the quality factor is 30. At 10 and below, it's 1. And then above 30, it starts to decline again. And that's called the overkill effect, where the particle is deposited too much energy, is just wasting the energy, is how it's described. It's a little bit more complicated than that, but I don't think you can read about it, but I don't have time now. So the most effective particles are in that region from about 100 to 200 kV per micron. And so that's important. So you can see the stopping protons. I'll point this out now. This will come up later. Neutrons, Phil mentioned they're indirectly ionizing. They make lots of low-energy protons, and they make the protons just at the right energy where that Q is going to be high, down around 0.1 to 1 or 2 MeV. These low-energy neutrons, they make all those protons, and they're going to be very high quality factors, or RBEs.
Risk is proportional to the quality factor.
Yeah,
okay.
And the dose, yeah. Okay, so here's the range, and then the beta block formula. One interesting particle is the triton, because the triton has a mass of 3 and a charge of 1, so Z squared is 1. So the triton has a range 3 times the proton, and the deuteron is 2, so it's 2 times the range of the proton at the same kinetic energy per nucleon. The other thing I forgot to mention is that we use kinetic energy, MeV, per nucleon, or per A, rather than total kinetic energy, because then all the particles you're talking about have the same velocity when you use that unit. So it's a good unit that everyone uses, even though people are sloppy about the terminology. You'll hear people say 100 MeV, and they really mean 100 MeV per AMU or per U. That's another thing I should mention, is that people will use MeV per U or MeV per AMU, but they're just really talking about per unit mass unit. You could put like Dalton. Biologists might say MeV per Dalton, which physicists would say, what's that? But it would really mean the same thing. But if you drop, when you're talking, a lot of people say this, MeV, but they mean MeV per AMU or per U. But really it's gone too far, because I've seen like a title of a journal article. Somebody sent me a preprint that we fund, and it said MeV. I said, iron 1,000 MeV. And I said, but you mean per U? Because it's totally different meaning. Because 1,000 MeV iron particle, if you don't have the unit right, is very slow. and it has a totally different meaning. Talking is one thing, but in a paper you have to be very precise. Okay, so what about neutrons? So they're not charged particles, so how do you slow them down and stop them? The only way is through the nuclear collisions. So they suffer elastic collisions and then nuclear reactions where they produce different particles, and when they do that, they give up energy, and that's the only way you slow them down. So when you talk about the range of neutrons, they're going to travel very far compared to a charged particle, because they don't have that charge to have the dE by dx to slow them down. Okay, so this is an example of what happens. So these are the top two figures are GCR energy spectrum on the moon or on Mars, and the bottom two are a solar particle event spectra for the 1989 event. This is the one I mentioned early this morning for my first year at JSC. We had the October, September, and August 89 event. People like to use the September one because it's a very hard spectrum. It has more high energy protons than a lot of other events, even though it wasn't as big as the October 89. So we can see what happens is a lot of neutrons come up, and you see that there's a pretty good neutron spectrum. The dash curve is solar max, and the solid is solar min. And then you can see the difference is that I also mentioned this yesterday, on the moon, you have those neutrons, but you haven't depleted the charged particles as much as you will in the Mars atmosphere. So relatively speaking, the neutrons aren't as important. And then on the Mars surface, because of the atmosphere, you really don't have a solar particle event problem. They're really depleted by the atmosphere. You cut them down in half by Mars itself, and then the 18 grams of vertical shielding, and then the atmospheric shielding all around. So, if they come in from this way, it's much longer than 18 grams of shielding, and it's like CO2, carbon dioxide shielding, so it really reduces them, and much bigger threat on the moon for a solar particle event. But you can see what kind of energies we're talking about. So if you remember the range curves, how much range, the range would be the thickness of your material, how much would you need to get past that GCR peak? So if you go back, so here you would need to get up to that like 1,000 MeV. You could see where you are. You need very thick shielding. And you need, for protons, you're going to need like 1,000 centimeters of shielding, of water shielding. So it's just impossible task. All you can do is modulate them a little bit and then worry about the nuclear particles. Okay, and then solar particle events, everyone's different. They're like snowflakes. So this is somebody, John Neely, who's retired now, that made this plot of, he just put every spectrum up to like 1990 on a plot. And you see each one is different. Most of them are like smoke alarms. They don't penetrate very far. The particles that are coming out, but there's a few of these, they're called major solar particle events, and you can see over 50 years since they started having good measurements in 1955, there's only like 10 of these super events that you have to worry about. So Nathan mentioned there's all kinds of CMEs every week, but there's not many of these major solar particle events where you have to worry about high flux and high energies. But there's lots of these little ones. Okay, so the shielding material, the stopping power formula, we realize that the Z over A ratio is the key thing, and then also the density of the material. And so the hydrogen has that Z equals 1 and A equals 1, so it's 1. And then if you go to aluminum, it's 13 over 27, so you're down a little bit less than 0.5. And most other materials are going to be around 0.4 to 0.5, so hydrogen wins. And then the other thing is the projectile fragmentation cross sections. I don't have time, but it's going to go like the mass number to a power like 2/3 power. So hydrogen can get more nucleons in the way of a GCR particle per unit mass than other materials, so it can fragment those particles. So in a thick shielding, fragmenting the projectile particles is good. So that makes hydrogen the best material. And then the last thing is the target fragmentation. So when the projectiles come in, you're conserving mass number and charge number, but the target fragments are coming out of, you don't have, conservation doesn't work. You just can, as many ones you hit, the more particles you're adding to the radiation field. So with hydrogen as a target, you're not knocking neutrons out, except for a more exotic nuclear reaction. We only can make one neutron, but if you hit an aluminum atom, you can make 14 neutrons if you fragment it. And you have all kinds of opportunities to hit all those different target atoms. So target fragmentation is a big part of the problem. Okay, so I showed these yesterday just to show you attenuation curves. You can attenuate solar particle events. Tissue modifies how well you think the shielding is performing. You really need to put tissue into the shielding calculation. And then quickly, just some nuclear scattering. Anybody have a nuclear physics background? So I really don't have time, but when you think about all the different ways nuclear reactions occur, I'll just give you some of the big categories. So projectile fragments, these are going to be fragments. There'll be a heavy fragment near the mass of the incoming cosmic ray, and it'll have a velocity that's like a Gaussian distribution near the projectile velocity, and then you'll have light fragments will have much more broad velocity distributions. The target fragments won't have as much energy. They'll be peaked down near like a few MeV per nucleon, so their LET will be high. They won't penetrate as far except for the neutrons and protons, a few of the other light particles. Now these light particles are produced in different ways. One is when you make a projectile fragment, there's a pre-fragment that evaporates particles to come to a stable state. So they're the evaporation. Then you have cascade particles. These are particles that are knocked out. They might get knocked back into the nucleus and cascade and knock out other particles. And then there's clusters of particles that are fragmented and knocked out. At high energies, you make pions and kaons, other mesons, antiparticles. And then elastic scattering is really you can ignore for charged particles because the d by dx is much bigger than the elastic scattering with the same outcome. But for neutrons, it's very important, the elastic scattering off the target nuclei. So we showed this picture of what the reaction looks like, the target fragments, the projectile fragments, and all kinds of possibilities. When you have one of these reactions, anything can happen. You can make any particle in the reaction as long as you conserve mass and charge. And in some sense, you're conserving energy, but you also have to remember that the particles are inside the nucleus are moving. So it's something called the Fermi motion. When you hit a particle, it could be moving towards you or away from you, so it could come out, in some cases, with a higher velocity than the projectile, and because it also has this additional energy from the Fermi momentum. So this is a cloud chamber picture of two very high, heavy ions, lanthanum and lanthanum, so bigger than the iron particles we're worried about, but you can just see how violent these collisions are. This would be what's called essential collisions, and each one of these streaks is a new particle being produced, and some of the streaks are going in the other direction, so they would be negatively charged particles, and most of them are bending the other way, so they're positively charged particles. Okay, so this is an example. So these would be, you have the absorption cross-section, which is a total probability of a nuclear interaction, but then once you have an absorption event, you can make different fragments. So this would be an example with iron particles and how the fragmentation event is now distributed. So you have from the projectile mass of 56, shown here all the way down to 20, but it goes further, and then you have different charges, and each charge and mass will have a different distribution. So when you talk about the shielding code, it has to be able to describe accurately that you have all these possibilities and how to assign the right weight to all the different possible fragments. And then I'm not showing here, but then there's also the neutrons and light particles that come off of these reactions. So if you make if you start off with oxygen and you made calcium-40, that means you had 16 nucleons that went somewhere else. So they could be neutrons, protons, alpha particles, and it has to balance out. And this would be another example of that. This would be this gives you more information about the velocity distribution of the fragments. So the very narrow distribution for each of the fragments. So each one of those spikes is a different charge group produced by the iron particle, and they'll have a very narrow distribution centered on the velocity of the primary iron particle in this case. Okay, and the other one is mentioned is the target fragments. They're going to be low energy, so they don't travel very far, but it's sort of like a cloud around the particle. As a fast particle is coming in, it's constantly making these low energy charged particles. In this example, if you look at the solid line, that's the primary GCR spectrum, and then these other curves, as a function of depth and shielding, show the prediction for the different light particles: helium, helium-3, tritons, and deuterons. And you can see it's what I would call is a quasi-steady state flux. So even though they're low energy particles, they don't travel very far. You're just continuously making them by all the fast particles coming through the shielding. So don't be deceived by the range of these light particles, because they're just constantly being made as the fast particles go through the shielding. And they just taper off slowly as you increase the shielding depth. This shows from 0 to 40 grams of aluminum shielding. So you always have these low energy particles. So why is that bad? And if they don't penetrate far, and you have this constant flux, if you remember, the LET of these particles is very high. So they're low Z but high LET because they're low velocity, and they're going to have high Qs. So that's why these light particles are a problem. So I said HCE before. This would be low Z, low charge, low energy, and they're important because they're high LET, and they're important because even though they have a short range, you're just constantly making them as the fast, heavy particles go through the shielding. Okay, so this is another example. Target fragments. You think you did really well with the liquid hydrogen. So this is attenuation for the solid cancer organ dose equivalent for 1 year in space. So millisieverts. So they all start off the same at 0 depth, and as you go into shielding from 0 to 40, you can see how that liquid hydrogen really absorbed all that radiation. But then you start to hit the tissue, and it builds right back up. So fortunately, you don't get back to the as bad it was with aluminum, but you can see you get about halfway back up. So so everybody remember now what happened here with the liquid hydrogen when it hit the tissue? Based on what I just mentioned. What's that? Well, the target fragmentation. So in the hydrogen, you had very little or no target fragmentation, just very small exotic reactions. You hit the tissue, you still have a lot of high energy particles, and then you start the target fragmentation all over again. And so it's still very good, liquid hydrogen, but it's not as good as you think if you don't consider the tissue behind it that you're trying to protect.
But this problem is always going to be there, right? No matter how much you reduce. It's going to multiply in the tissue.
Yeah. Okay, everyone knows the MSL, the Mars Science Laboratory Opportunity, is going to land on Mars in about 7-8 weeks, early August. So they'll be looking at what happens as all these charged particles interact in the atmosphere and then interact with the soil of Mars. And they'll have a rover and a base station, and on the rover will be the rad detector I'll show in a minute. So we want to be able to test how well can NASA and other scientists predict the radiation exposures on the Mars surface. So this would be the topology that you're dealing with, is that you'll have a radiation detector that's pointing up, and it will have about a 60-degree angle of viewing. And then you'll have the Mars atmosphere, and that atmosphere is going to change by what the altitude of the instrument will be. So there'll be some variation of the dose just by the altitude of the atmosphere, much more variation than we have on Earth, because the atmosphere is very thin compared to Earth's atmosphere, which is saying 18 grams versus 1,000 grams for the Earth's atmosphere. It is from a paper we did a long time ago, just showing you that the downward dose equivalent, ignoring the upward from the neutrons, just to show you how much variation you would have over the surface of Mars. So it's about a little less than 20 millisieverts per year to a little more than 30 millisieverts per year would be the variation, just because of what your your vertical height would be relative to the atmosphere, or where you are on Mars. That's going to vary. So if you go into one of these big craters, you're protected by about 50% relative to a higher elevation. But unfortunately, I don't think NASA wants to pick a landing site on this premise because it's really about the science. You're going there to do the science, so if you have to worry about picking the landing site for radiation protection, that might be conflicting with your science. I don't show here, but there's also the idea of lava tubes. So you can go to these planets and go down to the lava tubes. So you're like a mole. You go all the way to Mars, and then you're a mole for 18 months. So, or you can say, well, I'll just go down there part of the time. But so it might. But then the less time you spend in those lava tubes, the less protection you're getting. So unless there's some good science down there, and it probably is. But
can't you find a cave or an overhang and reduce the risk?
Yeah. So you can put your vehicle next to a thing. I'll show you. We have an example of analyzing that. So, okay. And then I mentioned this yesterday. The neutrons are very sensitive to soil composition because the interactions depend on what material you're hitting, and these lower energy neutrons below 100 MeV, which are going to be the ones more damaging because they'll produce lower energy protons, which have a high LET, are going to be dominated by the upward flux rather than the downward flux. At least that's what the predictions are. And hopefully the RAD detector will help us verify some of that. Okay, so this is just a plug for RAD. And interestingly, there's a gamma ray source on the rover, so that's something that they're contending with, is how to reject the gamma ray source dose from the GCR dose. But they're doing a good job. They've measured some of the solar particle events that Nathan's showed this morning. The RAD detector also has measured it in transit to Mars, and they do some good correlations with the GOES detectors. Okay, so shielding due to the planet topology, we did this for the moon, where we looked at different craters and how much protection based on the depth of the crater. And you certainly can get something on the order of 10 to 20% protection by picking the right crater to park a habitat in. And I'm sure there's going to be certain things on Mars' surface. And then the best would be, could you park up against a mountainside, and you might be able to get up to something close to 1 pi shielding, in addition to the 2 pi that the planet presents. So the way we look at this in the HC-TRAN code is, because we're not doing particle by particle interactions, we're just doing densities as a flux, is we do what's called ray tracing. And in JSC, Pro-E is usually the engineering standard, so we developed this tool to ray trace within a Pro-E design. And we had a company, we started the project, then we had a company finish off, and it's called the Fishbowl Ray Tracer. So you can use this. The idea is you're going to pick a dosimetry point, and then you're going to shoot out rays in many directions as possible to get to convergence. Usually takes about 1,000 rays to have convergence. And along the ray, you're going to track how much material is there, and then also what types of materials are there. And then what you do is, for your HC-TRAN code calculation, is transport the particles along that ray to the dosimetry point. And that's fairly accurate. So it's kind of interesting because the Monte Carlo codes that I mentioned, they can't use ray tracing, and they do a good job with all the angular effects, much better than HC-TRAN. They take much longer, but then they have to massage all the data to some simple object. They can't put in all the details of the spacecraft like we can with HC-TRAN with this ray tracing tool. So it's kind of, Monte Carlo has the ability to do all the angular distributions and everything, but they don't have the ability to map that to a very detailed vehicle design. So we can do ray tracing on a design with thousands up to 10,000 parts and still be able to converge very quickly.
So is the point you pick, is that arbitrarily chosen, or is that like on the organ of the
yeah, you
crew
just
member,
generate
or-
as many points as you're interested
So
in.
you have to discretize that volume and put them wherever you want?
Yeah, you know where the crew would be. You could just let the computer do as many points as you like. So,
And I had a question, does clothing do anything, or does it just go right through the clothing?
It depends. Like
Like the
the
fabric?
less shielding the vehicle presents, the more important the clothing is, and the more shielding that's already there, the less important, because it just becomes a smaller portion of the ray.
But
Yeah.
say, for example, would it be possible to get any attenuation from a good suit or something, in terms of
If you're on a spacewalk or
Right.
EVA,
Right.
it's an important role to reduce your skin cancer
Right.
or skin dose. Is the clothing, and for the internal organs now it's just a small fraction of what the body might provide, so it's less important. So, and then you can do iterative designs. Like one of the things you'll learn is that shielding, the benefit shielding is going to be follow like a 1/r² law. So the farther away the shielding is, you might have a hot spot, and you want to cover up that hot spot like a window. And so it just really depends on how far it is from you. So you can do iterative design with this ray tracing tool to quickly evaluate what's the benefit of like retrofits or spot or partial shielding of a vehicle, rather than trying to shield the whole vehicle. Like in these type of capsules, the heat shield is very thick, so you don't have to worry about that direction. You might worry about the windows and other aspects. And so this is another example. And actually, once you get a feel for the design, you don't even have to do the transport calculation. You can just look at these thickness distributions of what fraction of your shielding has some minimal thickness, and that's a good way to quickly analyze what the retrofit's going to do to try to pick up where the weak points are on your shielding distributions. Yeah.
I'm just wondering, has there been a study where you vary the geometry and see if there's any sweet spots or how that changes? Because most of the time the crew member will, and I'm asking this because most of the time the crew members will be in the deep space hab, and currently, that's supposed to be cylindrical.
Yeah, we've done like conceptual designs. There's a fellow in my group, Hatem Nanu, but he's our lead on this ray tracing. I can actually have him send up a pitch where he's done some conceptual how do you find a weak spot and then cover it and show what the benefits are that to minimize the mass of augmenting the hot spots. So that's been done conceptually for a few examples. Okay, and this is just an old example from the ESAS study where we were looking at could you shield 4 times the 1972 event. So the 1972 event is about the highest one we know about, but we wanted to see, well, maybe there's a worst case that's farther up the scale. So what would it take to go 4 times that level? Question, yeah.
Just in general, is there like a threshold velocity before the component becomes less, the nucleon becomes less harmful to humans? And then is there like an average number of collisions before this happens? Well, obviously depends on mass.
So I gave you the basic idea is the range, in the range, and then it does take into account. Yeah.
Regardless of density, regardless of material itself, it would just keep.
Well, the y-axis on those curves had the density as part of the formula, so it's part of the result, the density. Yeah. And then the nuclear interactions, I mentioned this yesterday. For an iron particle, it's about 1 every 10 grams per centimeter squared, or every 10 centimeters of water is about the average mean free path. For protons, it's more like 30 centimeters of water before it undergoes a nuclear reaction on average. So it's changing with the particle type and the material that you're going through. Okay, so this shows you can look at in this case it was polyethylene, augmenting that early version of a lunar transfer vehicle, and you can see how much polyethylene could reduce the cancer risk down to a low level. So this even like 5 grams inside that vehicle was gave you a good return. And then this also, if you didn't pay attention, I didn't point out, this was that early CEV versus the Apollo. So it was already doing much better than the Apollo capsule or the Apollo command module for how much inherent shielding it was providing. It's just some more examples of that design. 4 times the 72 event versus how much augmentation of the polyethylene you would put inside the capsule. So as little as 2 grams got you down to below the risk limit, but not at the 95% confidence interval. But then if you got it about 6 to 8 grams of polyethylene, you were below that cancer limit for 4 times larger than the biggest event we knew about.
That's just for SPE, or is that?
Yeah, this is for the SPE problem. Okay.
Are there any ways of attracting radiation? So could you like attract it to one place and then therefore it wouldn't go to another place?
Yeah, so a negative charge will attract because it's all positive, but you would need a big negative charge, I guess, because it still has a very high velocity. So that's something to think about. Yeah.
So on Sunday, Dr. Howard was talking about a toroid that would protect the, I guess, habitable environment by deflecting it using Lorentz forces. Could the opposite be used too? So using a toroid that has like he put like 10 Teslas as their, what do you call it, their toroid. But could you do something in the opposite manner of that and protect like a certain area? You just put it in a circle? Well, for at least the charged matter, not the neutrons. But.
Yeah, there's probably something to pursue there. I think because the magnet designs, you can develop different systems of magnets and plasmas that have different fields. And so I'm not an expert in that area, but I think there's ways to design around what you're suggesting. Yeah.
Let's see. This hasn't come up yet, and there's probably no answer for it, but what about dark matter? I knew you'd laugh, but it's supposedly, 85% of the universe, and don't y'all need to figure that out and see how you can use it?
I guess it follow the beta block formula.
What?
Should it follow the beta block formula? Is it? I don't know. I haven't thought about that. What is it? Neutral charge, or it must be neutral charge? Right?
Well, I don't know if we know what it is. That's why it's called dark matter. And yet it's what from the calculations that physicists make, it's 85+% of.
But we're in a sense we're already taking it into account because the cosmic rays are coming from all over the galaxy and they've gone through all this dark matter. I guess it would be really bad if the dark matter wasn't there.
Well, but if you could figure it out, you could use it as a shield. Maybe
Oh, we are. But that's what I'm saying. We are.
What can I say?
Yeah.
I brought it up. It's the answer to the problem, actually. We just don't know what it
Yeah,
is.
you're acting like an anti-climate problem.
Yeah. So this is just to point out, remind you the densities of some of these materials leads to a different range of physical thicknesses. So this is an example of looking for a 20 gram per centimeter squared shield, but picking different materials. And then what does that result for physical thicknesses? And that would be important because some of these materials you would have to house in some kind of vessel to contain it, like the liquid hydrogen or the methane. So the methane might need a different vessel, much smaller vessel than the liquid hydrogen. And you also have to consider about the pressure and the temperature of the object. So these would be additional considerations. So the liquid methane looks interesting, and that's a more common fuel for rockets. And then this would be examples of how well those materials do for different thicknesses. And at solar minimum and solar max, where for solar max we include that 72 event again.
I'm going to try to top Jack's stupid question with it and see if I can get galactic cosmic rays. Aren't they colliding with each other?
It'd be very infrequent because the density is so low. I mean, it's plausible, but it would be very infrequent. So.
Could you make them?
But they were all over the place, right?
No, it's still very, very. Because you think of like 10 to the 23rd atoms, Avogadro's number, and then there's about 10 to the 8th particles per centimeter squared per year. So, and you have a lot of Avogadro's number in a centimeter squared, so it's a very low density gas, the cosmic rays compared to a solid. So about angels, there's lots of angels. I think with time there'll be more angels.
But a head of a pin is large.
Or rabbits, because rabbits, you would just have a population of rabbits. They become your shielding as the mission goes.
So did I type that question?
Yeah. No, I mean that's an interesting question. But I remember you were at Langley. I was at Langley, and they had us as they didn't have physicists, so we were atmospheric sciences, and then low density atmospheric sciences, because the density of the cosmic rays is so small compared to what the other ones at Langley, other atmospheric scientists were discussing.
How fast does the shielding degrade? Because isn't a consideration that in order to get to Mars, the shielding should will eventually be broken down pretty much?
On the surface, you have like UV and the solar particle events, because all these solar particle events will have lots of low energy protons. So most of them don't have high energy protons, so they don't penetrate. But there's a lot of low energy proton dose and UV, so there is surface degradation. But just for the same reason I mentioned, when you think about Avogadro number and how many of these particles per year are inside a material, it's a very small effect. So same with like food. I know people in my building are always saying radiation might cause food damage, but no way, because the FDA and international bodies let you irradiate food to get rid of microbes, and it's safe up to like kilograys. So like huge doses of radiation are used to irradiate food for protective purposes, and there's no way that these low densities of particles are going to be harmful to food. So it's really about special kind of things like cells, DNA, oxidation that causes signal transduction in cells. And you have a few events cause big effects. And it's not something like an inert object where you have lots of repetitive molecular bonds, and you're only going to be breaking a very small percentage of those molecular bonds. So it's really going to be much less in the impurities of the material that you start with. So.
These particles go straight through us. So how good would I be as a protector for somebody else?
Yeah.
Got this image of taking dead bodies up there and making like.
Yeah, that's a legitimate thing, because it's like the 1 over r squared. So if you're close, you're going to be providing shielding. So they don't.
They could have
the
all
solar
DNA
particle
damage and then
solar particle events don't go through you because they're not that energetic. But the nuclear particles are more likely to fragment than to go through you, because I mentioned the mean free path is like 10 centimeters for heavy particles and 30 centimeters for water, and a typical cross section through your body is going to be less than like a typical deep-seated tissue is 10 centimeters, and across your body might be 30 or more centimeters, depending on the direction. So you're more likely to have a nuclear reaction than the particle to pass through you.
Basically, does this prove like abiogenesis, like spontaneous life? Because like if you have like all these massive particles just going all over the place, if you have a rock thick enough so that it penetrates but just stays inside of the lattice still, you got carbon, you got iron that decomposes down to like carbon, hydrogen, oxygen, whatnot, and then with more radiation, you irradiate it and it creates chemical bonds between them. It can either promote them or destroy them, right? So if it promotes them, there's the off chance that you could have some kind of microorganism from all these bonds. So is this possible? So that's what it sounds like. Listening to both these lectures.
Oh. All right. Okay, so but anyway, this example, just
I notice epoxy is listed up there. Is that really a possibility? I mean, it does have hydrogen in it, so that's one of the requirements. But do you think that could be used? How does that stand
yeah.
up?
Well, this shows it's not very useful for shielding. So but we threw it in there just to be something different. Graphite epoxy.
Mm-hmm.
You can see it's not that much different than aluminum.
So, is there any kind of
Welcome to WebEx.
you think you've exhausted the possibilities in terms of materials that could be used for shielding? Is there something, maybe like when you think of like carbon nanotubes and so forth, obviously not carbon itself, but could you make something that had, like a hydrocarbon based on that? Also, are there?
Oh yeah, I think you could, and there's some benefit. It's not negligible, but it's not it's not like a magic bullet. So CH4 is a good example. If you can get 4 hydrogens per carbon, then you have something that's more practical, and it's providing some benefit. I'm not sure if you can get 5 or 6 hydrogens per carbon with a nanotube, but if you could, that would be beneficial. But this gives you a range. You can see the problem is these materials do very good for solar particle events, but you're not doing too bad with water. So it becomes a question. You might have water aboard already that you can use as a storm shelter, so maybe you don't need to do anything extra. And it does a little bit better for cosmic rays, but not earth shattering. Except for the liquid hydrogen, that is a nice reduction you get there. Okay, so we sent the links, and we're evolving these computer codes, but hopefully I'll give you a background of these are very easy tools. People in this room today could learn the HC-Tran either on the Langley or our website, and then get some other tools about ray tracing and can do some of their own designs within a few weeks. And then there's also these big Monte Carlo groups, Geon 4, Fluka, FITS, that are a little bit more cumbersome, and you need to be on more high-powered computer platforms and take more time to run the codes. But they also have training schools as well. Okay. All right. Okay.
Thanks, Frank.
Yeah.